Alrighty, I guess we can go ahead and start. So welcome everyone. I am Blaine Carter. I am going to be basically session support. Can I say that correctly? On this office hours session, and I will be watching the Q&A and helping basically monitor questions for beta to answer. If you do have a question, you should see down at the bottom of your Zoom screen, there should be a button that says Q&A. You can click on that and ask your question in there, and then we'll either type an answer back, or Beta will just use his giant brain and answer the question normally. Obviously, the expert here is Beta. You can see his Twitter handle down there on the screen, and he has a blog site. You can go read up on stuff. Before we get started, if you want to go reproduce these examples, Beta will be running the examples in Oracle's LiveSQL, and there'll be a link to that at the end of the presentation. So if you hang around, you can get that link. And then if you just want to run these in your own free database, if you haven't already seen this, Oracle is operating some free cloud services that you can get from oracle.com/cloud/free. And so with that, I will turn you over. Let me find the stop share. I will turn you over to Beta, who is going to talk about how to apparently use JSON data to get us to the moon or something along those lines.
Hey,
anyway, Beta.
Thanks for the great introduction. Yeah, that's a talk I always wanted to give, and I finally put together the things. Let me start sharing my slides. And if you have any questions, just put them in the Q&A. And Blaine, hopefully you just interrupt me, because I won't be monitoring the Q&A window here. So just stop me, and we'll see if I find a good answer. So can you see my screen here?
Yes, I see your screen.
Oh, wonderful. So we've had a lot of presentations in the past where I was going through some very specific JSON features, how to query it, how to generate it, etc. But this time we want to really take a look at what does it mean to work with a hierarchical data model. And JSON is just one example of a hierarchical data model. And this is going to be a little history lesson, hopefully entertaining. So we're going to look into a data model of a simple application. So we're not looking at the application code, but how we want to persist the data to support the application. And we basically take two views at it. One is a plain relational view that will be a little bit boring, I guess, because it's everything you already know. Then we look at a pure JSON modeling use case. This is if you didn't have a relational database, but you were using a NoSQL store or a document store that has great support for JSON, but may also be quite limited because it's built around the hierarchical data model. And then we look at a combination of both and try to combine the features of both JSON document stores as well as the relational model. And the goal of this presentation is not to poo-poo one solution or to say you need always this, but it's rather to create some understanding of the different characteristics of each of this model. And the scripts are available on LiveSQL. So what I'm presenting here, you can follow it if you want right now. One thing I've observed, so this is our LiveSQL website. You go to LiveSQL Oracle.com and you can look for different scripts. So if you search for moon landing or JSON data model, you should be seeing this. And then the script shows up, and then you click on Run Script. And then it will take quite a while, maybe 30 seconds before you see the result. And there is no progress bar or anything. So don't assume it's crashed. The results will be coming. So let's go back at the slides here. We're going to start with a use case that all of you are familiar with, and that's a school environment. So in the simplest case of the school, we have a bunch of students, and students attend courses, and a course is given by a teacher. So I think this is something that everyone gets. It could even be like an after Tom. Right now you're the student, I'm the teacher, and the course is JSON data models. So in our application, what could be typical operations? Well, obviously, we would want to insert students or teachers or courses. We would perform update operations, for example, enrolling a student into a course or changing some attribute values. Let's say a student gets married and we have to change its name, or a course state needs to be modified. Then there's also queries. So for example, we want to find students which have not attended enough courses, or we want to find out the teachers of a given student. And our application may change over time. So we also want to look at the schema change aspect of it. So Blaine, is it your keyboard I'm hearing?
That would be me. Sorry, I was taking notes.
Okay, maybe you could.
I usually forget.
Just mute yourself or type a little quieter.
I'll mute. Sorry about that.
Not a problem at all. Okay, so one way to model this would be a entity relationship model or an ER diagram. So we define the entities of our application, and they would be a student and a course and a teacher. And then we have different attributes for each of these entities. So a student can be identified using an ID, and a student has a name, and maybe they go to a specific grade. And there could be a lot of more attributes. This is not about completeness here, just to understand this model. And similarly, we have attributes for a course and a teacher. So a teacher could have a salary, and a course has a name and a start date and an end date and maybe a capacity. That's the number of students that are allowed in that course. And then we span the relationship between these entities using these diamond boxes. So we say a student attends a course, or in the inverse direction, a course is attended by students. And similarly, the teacher teaches a course. And last, we add cardinalities to this. So we say a course is always taught by one teacher. So if we go the direction from course to teacher, we see that there is the one here. So it means the course has always one teacher in our model here. So if we had a course with two teachers, then this model would not be correct anymore. Then there would also have to be an M here, for example. But here we limit it and say every course is only taught by one teacher. In the other direction, from the teacher to the course, we have the N, which means one teacher can teach more than one course. So for example, math and physics and biology could all be taught by the same teacher. And the other relationship here between student and course, I think, is also quite obvious. A student ideally attends more than one course, and a course is typically also given to more than one student. So we have an N-to-M relationship here. That's actually a quite common approach. I'm not so sure these days, but when I went to database courses a long time ago, that was a very simple way how you could define the model for your application. So the nice thing about this model is that it translates very easily to the relational model. So you could say, well, every entity maps to a table, and the attributes of my entity, those are the different columns in my table. And whenever I have an entity or two entities with a one-to-one relationship, those can be combined in the same table. We don't have such thing here. We only have a one-to-N and an N-to-M relationship. But assume we had an entity address, and a student could have, or a student has one address, then this address information could be combined with the student information. So the columns for the address would be in the same table as the student's name. If we have one-to-N relationships, then we use references. So we use the same IDs or foreign key primary keys there. So the course refers to a teacher. And the reference is expressed by same column values. So we have an ID for a teacher, and then the course uses the same ID. That basically materializes this relationship. And if we use primary key and foreign keys, then the database can even enforce that the values match. So a course would only be valid if its teacher really exists. And if we have N-to-M relationships, then we use a mapping table. So the example is here, we have a student attending a course. And now let's go to the practical part. We take a look at how this looks in LiveSQL. I think I can close this one if we go to the other one. So here I've already executed it so that we don't have to wait for it. So for this relational model, I create these different tables for each entity. I have my table for a student, and the student has an ID, and I just said it's a first and a last name and maybe a grade. And I have my teacher table. Teacher similarly has a teacher ID, also some name information and a salary and the join date. These attributes don't really matter, just showing that the tables are not exactly the same. And I have my course table. And now this course table, besides having a own ID and a name, now it also uses this teacher ID here. So this is what we're going to use as a relationship to build on. Now this is this is basically the example for the 1 to m relationship that we use this ID here. Now for our n to m relationship, we have this table to express this n to m relationship between student and courses. So I call this table attends, and a student given its ID attends a course given its other ID. And then in the relational world, it's quite strong to enforce these constraints. So I'm adding primary key constraints for student, teacher, and course. And also on my attends, I use a primary key, which is the combination of student ID and course ID. So that combination should be unique. The same student is only attending the same course once. And I use my foreign key constraint on the course table, and I say, well, the teacher ID in the course, that points to the teacher table and the teacher ID here. So now if I do some more constraints here, I basically complete it. So I also do constraints on the student, that the student ID in the attends table points to the student table, and similarly that the courses. So this is just to make sure we're going to see if I insert something that the data is really valid. So now I'm inserting myself as a teacher here. I'm very motivated and idealistic, so I work for free. My salary is 0, but it was hard to get Blaine, so we had to pay him quite some money. So now we have 2 teachers, and we have courses here. So the database course, so you see T1, that would be me, and programming, oh, there's a typo here, programming is taught by Blaine. And we also see that it's quite easy to insert a course without a teacher yet. I mean, these are all pretty trivial examples here, and you may ask yourself, why is Beta showing all this really easy, trivial stuff? And you're gonna see why I'm showing it, because the stuff that looks so easy here might actually get a bit more complicated if we go to a hierarchical data model. So the point here is it's quite easy to add a course where we haven't found a teacher yet. So we know there will be a course math, but well, we haven't found any teacher yet. So the value for teacher and the start date and end date are null. Here comes some students. We have Mickey Mouse and Donald Duck. And now we insert the relationship in our attends table. So student 1, that I think was Mickey Mouse, is attending course 3, and course 3 was programming. And similarly, we add some values for the other student. And now this is an example where we want to put our Mickey Mouse student in course number 99, and we get a rejection here because there is no course 99. So with this model here, with these constraints, we are pretty safe that our data really makes sense, that we don't have dangling references to data that's no longer existing. Similarly, I could not delete a teacher if there is still a course taught. Good. So another trivial example here is finding lazy students is quite easy. Those are students who have not enrolled in any course. So I'm just querying my student table, and I do a subquery where the student cannot be found in attends. So I'm using this not in, and I see that Donald Duck is a lazy student. And if I want to find out every teacher of a student, so this is student S1 is Mickey Mouse, so I want to find out who are all the teachers that deal with Mickey Mouse. Well, this is a join between the student table, the teacher table, the attends table, and the course table. So I do a join. For this query, I need to join all my 4 tables and express some conditions that at the end I am filtering the teacher names for a given student. I'm not going into the details here. I think you can do this yourself since the course is available. Now, updating a course is also quite easy. There is only one row we need to update. So if I want to change my math course into algebra, it's a very simple update operation. Now, if we go to schema changes, we're seeing some interesting things. So first of all, adding a property is relatively easy. I can do alter table course and add something like the credits that are given if you successfully finish the course, or maybe capacity, how many people can attend it. So this is a scalar value that is being added to one of these entities. That is quite easy unless you use select star. But if you specifically select the columns in your queries, then these queries can run as they are. But now we have a schema change where the cardinality is not 1. It's not a scalar value. For example, let's have some information about which languages the teacher is speaking. So let's say I'm speaking English and German. Blaine speaks another set of languages. So we just want to have this information part of our data model. That's a schema evolution case here. And now this is getting interesting because a teacher could have multiple languages. So one approach would be to introduce different columns here. We say there's language 1, language 2, language 3. So this would limit us to 3 languages that a teacher can speak, but it would also mean that if we want to find out who are all our Spanish-speaking teachers, we have to look into each of these different columns. The other solution would be to introduce a new entity, which is the languages that a teacher is speaking. And we would have another N-to-M relationship table here. And now if you want to find out the information about a teacher, you would have to actually go at 2 tables. One is the teacher table, and the other one is the teacher languages table. And similarly, if you wanted to insert information about a new teacher, you would now have to disassemble this record of information and insert some pieces into the teacher table and some other pieces into the teacher languages table. So this is a bit where I would say this motivates the use of JSON, where people say, hey, my schema changes too often, or I don't want to disassemble my set and put it into multiple tables. I want to have it all together as one big JSON. And now we're going to go back to my slides here and look at hierarchical data models. Any questions so far? Maybe, Blaine, was there something?
Not so far.
Wonderful. Good. So now we look into hierarchical data models. So JSON is just one example of a hierarchical data models, and I want to, my goal here is to really show the characteristic of hierarchical data models. And the first real hierarchical database was IBM IMS. And that was built in 1966 as part of the Apollo program. So when the US decided to send someone to the moon, they had to build this massive rocket, which needed a vast number of parts, and they needed some database to just capture the complexity of these parts. So they went to IBM, and they came up with IMS. And we're going to look on the next slide. We look a bit at IMS, but this is just one example. And since then, so this was 1966. Then in 86, there was SGML. Then there came HTML, XML, JSON, YAML. So there's a bunch of these new hierarchical data models. And maybe it's time to come up with the next one. Maybe someone has a good idea for the next hierarchical data model. They would all probably share more or less the same characteristics. So one thing that I want to point out here is that some of these models allowed the use of references. So for example, in HTML, you could have a link to another page. So every HTML site is a tree. But then with these links, you could span a graph. Similarly, there was Xlink and Xpointer for XML. But the question really is that truly a manageable graph? Because, for example, in your HTML page, you could link to a page that exists today, but nobody is enforcing that the site still exist, right? You could have dangling ref, someone removes the HTML page you're linking to, and your document would be incorrect. So this is why in most cases, these data models remain as trees. Even with XML, which had Xlink and Xpointer, the vast majority of documents that I've seen still were kind of self-contained, meaning they tried to get all the information in one document. So this is now in the 70s or 1966, this is how computers looked back then. And you see an example here of IMS. I was lucky to find a similar example with a school here. So they said, I have my course. I put this little text at the bottom saying that the database record exists in a hierarchy, and they call these sub-things segments. So the student would be a segment, for example. And they say here the course segment is at the top of the hierarchy. The other types of data in segments would be meaningless if there was no course. So this means I need a course to enroll a student. So a student cannot exist without a course. And then people created workarounds like the default course or the non-existing course just to be able to put a student underneath. So there is quite some limitations of this model, and we see that they share this limitation with JSON. So how would a pure JSON data model look like? And obviously, people could now say, if I come up with a model, it could be inefficient, and I could have come up with a better model. So I kind of Googled a bit and found a document store, a JSON document store, which advertised this model to reflect the data structures of the university. So I have this is the paper they published, and there's the link at the bottom so you can download it. It's quite an interesting paper. And you see that similar to this IMS slide that I've shown previously, they have the self-contained record, which contains information about a student and the courses that the student is attending. So if we look at it, there is a ID for this record, and then they say, well, this record, that's its role as a student, so I could assume that there is another role, which is teacher, and there is information about the specific student or teacher, and then we see the courses that the student is attending, and you see that inside the course, so this is not only like a list of references to a course, but it's actually having the information about the date when this course starting and ending, as well as the name and the title and additional properties of this course. So let's play with this a bit in LiveSQL. So we're going back to our session here. So I called this the pure JSON model. So I'm creating a table university here, and I'm storing my JSON data as a Clob, and I'm using this isJSON check constraint to make sure that whatever I insert is actually syntactically correct JSON. So similar to the previous or to the slide which shown this model here, I insert a record. This is a student, and the data, this is my Mickey Mouse. And inside I have the information about the course. So Mickey Mouse is listening to databases and programming and math, and the properties of each of these courses is part of this array. And I'm adding another record. Maybe I should have had another student here, because then you would have seen if two students are attending the same course, then you need to repeat the course's name and the start date and the end date. But now we do have the teachers. Actually, you see the repetition already here with the teachers. So I'm inserting a teacher here, and you see that the role is different. So the records look the same, just the value for the role instead of student is teacher. But now for databases, you see the course ID C1, we repeat the name of this course as well as the start date and the end date. And any other property for a course would have to be repeated in these records as well. So this is Blaine, he teaches programming. And now it's quite easy. Now we do the same, we run the same queries, like how would we find our lazy student? Well, that's still relatively easy. So I'm doing this now in SQL here, but the document stores typically have similar means of expressing such a query. It may not be SQL, it could be another way to express it. So I'm using just SQL here, but in our SODA API, which is our document style API, this would be the query where we say, well, go to the course and then perform the size function and compare it with 0. It would actually rewrite to a SQL quite similar to this, but we see that it's easy to find that Donald Duck is our lazy student because his course array has the size 0. Now, now we want to do something that was very easy in the relational world, which was to update the course of the name. So remember, we had this course called math and we wanted to call it algebra. And the issue is now here with this data structure is that the name of a course is repeated for every student that attends this course, as well as for the teacher that is giving the course. So we need to, for this rather simple update, which was a one-row update in the relational world, we now may have to do multiple updates. Multiple documents may need to get updated. So this is something that could obviously be done in SQL here, but this pure JSON use case is meant to kind of model what you would have to do if you didn't have SQL. So in the SQL world, we could say, well, we disassemble it, we do an update, and we reassemble the same JSON. It would not be beautiful at all, but it would be doable. But here I'm trying to simulate how this could be done. And I figured out that this might be an example where people actually have to write custom code, where this is something that the application has to do. So I simulated that just doing in PL SQL code. So what do? We have a function, and so we cannot use a declarative way of expressing the update. We have to really hand code it. So I created a function called update course name. Well, it parses the JSON, it goes to the array, then it iterates over the array, and then it extracts the course out of the array. So we have an array of courses, and then if the name matches, then we update it with a new name, and at the end we turn it back into JSON. So you see here, I'm calling this function update course name on my records, on my JSON records, and I say rename math to algebra, and you see here that our course C4, which had the name math, has now the name algebra. And if we had more records, all of these would have been updated. And so you see here that something that was extremely easy in the relational model already creates some complexities if I modeled my JSON that way. Something I just want to give as a teaser for one of the next Ask Tom, we have a new operator to perform this update operation in SQL. That's a 20 version, and LiveSQL is still a 19. This is why we get an error here, but you could also, the same stuff that I've written in a code could be expressed in SQL using the JSON transform operator, where I give it like a predicate and a right-hand side where I give it a new name. So this is just something maybe I do one of the next Ask Toms on the news in 20. So finding all the students of or all the teachers of a given student is similarly non-trivial if you do not have SQL. It may be something where, again, if you have a document store, you may have to solve this in your application code. We have JSON table in the database, so if you, for some reasons, I mean, some use cases allow you to model the JSON data, then I would say, well, be aware of the properties of the hierarchical data model. But in some cases, people have to process data that just has this sort of structure or this nature of repeating data inside. So it is still possible to query that in SQL using JSON table. So what I do here is I use JSON table and I project out all the information about a student and the name. So for example, I project out the role of a person. So I'm seeing that this is a student and teacher. Then I project out the ID of that person as well as the name. So this way I can flatten my JSON into a relational structure. And that's a bit of cheating actually, because now I'm back in the relational model and I obviously have all the strength and features of that SQL offers me. So with this, I'm using now this query in the with clause. So this is basically just flattening my data. And then I can use a self join. So I'm using flat JSON for my students, flat JSON, so the same subquery for my teachers. And then I can express a join condition where I say, well, the student user role is a student, the teacher's user role is teacher, and now my student course ID is the teacher's course ID. So this way I can, so this is the course ID here, I do a self join on this table, so this way I'm able to find out who are all the teachers of Mickey Mouse. But again, that's kind of using SQL as a fallback. If you use a NoSQL store that doesn't have it, you're again a bit on your own here. Now, if we look at schema flexibility, on the other hand, the thing that was quite problematic in the relational world where we said a teacher could have multiple languages, that's now very easy here. So I'm adding another teacher here, Stephen F., and he speaks English, Spanish, and PL SQL. So this does not impose any problems at all, and it's even trivial to query it. I can use my JSON exists and go to my languages and compare it with Spanish, and I find the record here. Again, I'm using SQL here, but document stores have other ways to deal with it. So we're seeing here in this pure JSON model that things that were very easy in the relational model are quite hard here. And on the other hand, things that were hard in the relational model, like schema evolution, are really easy in JSON. So let's go back to my slides here. So if we look at this model, just to summarize it, if you model your JSON data like that you have to repeat information, you have the problem of updates being more expensive because you have to update all the occurrences, and also inconsistencies are possible. So the IBM IMS at least was transactional. A lot of document stores are not transactional, so then you even have to handle inconsistencies in your application course. And there are these model problems. I figured this one out if this one question here, let's say we wanted to put a capacity on a course. Let's say math can only be attended by 30 students. How would we even do that? You basically have to, the course information is scattered around. So every course would have to say max capacity, and against which one are you checking? If you want to add a new student, are you looking at the first occurrence of another student having the same course and then you pull the capacity out of there? That just seems quite odd. Good. Basically, the way I called it, this is IMS. So if you use JSON this way, you just did a time travel. You get yourself a little time machine and you entered it and you set the timer to minus 50 years. And you basically are back in the IMS world. And these deficits here, like the deficits I'm pointing out in these yellow boxes, there are a couple more, I wanted to keep it easy, are exactly what motivated the relational model. So there was this guy, Edgar Clob, and in 1970, he published this paper on relational databases. And IBM was making so much money with this IMS thing that they didn't want to implement it. They basically said, nah, that's great, but we're not going to do it. And then a young fellow named Larry Ellison found this paper, and he saw the potential in it, and he implemented it in a company called Relational Software, and they called their database Oracle database. And that's basically the story here of how the relational databases came into existence. It's really interesting that IBM didn't see it. So now the question is it possible to combine some of these properties that you don't either go into 50 years back IMS world nor in the very rigid relational schema? And the main idea I want to show here is to basically combine the schema flexible JSON with the relational model. And the main idea is to basically keep your entities in separate tables. So what we've seen in the pure JSON model is that different entities, teacher, course, student, were all mixed up. And because they were mixed up in a hierarchical data model, you had to define the hierarchy. Who lives on top of who? Is the course on top of the student, or is the student on top of the course, and where does the teacher belong? So the moment you store your entities in separate tables, you totally avoid having to answer that question. And since you are in a relational database, you can use SQL joins if you want to have, if you need access to multiple entities. You can still use all these relationship modeling using IDs, primary key, foreign keys, etc. And you use JSON table or JSON value to extract data from the JSON to the relational model. So if you have some queries that need to run very often and which need joins on different entities, well, you could say, well, I'm just using the materialized view to make that a bit faster. The other example is that it's not even a full, how do I say this, puristic question here. There's even the idea that you say, well, I'm really mixing even my relational model even further by saying like the fixed columns, like ID columns, maybe timestamps, things that I know will always exist for my application. I could still model these relationally like in a normal relational application, and only those fields or those parts of the application where I believe will be more prone to schema changes, I could say there is also a JSON column, which I use for schema flexibility. So let's look at this in LiveSQL. Any questions so far? Interrupt me.
Not so far.
Good. I hope that's good news. I hope I haven't lost everyone. So now we're going here, and I'm creating now my different tables for my entities. So for my student entity, I have my student table. And I'm not really using a flex field approach here. This is really, I have an ID which identifies my JSON record, and this is my JSON again stored as a CLOB. And I do the same for my teacher and for my course. I don't need the attends end-to-end mapping table because I can use a JSON array for that. So I'm living with one less table. And I'm also adding a primary key on my teacher table. I could have probably should do the same for the student and the course as well, but I'm only doing it here. So there's something in the chat. Okay, I'm talking too fast. Good. Okay, wonderful. So now I'm putting in the teacher information, and you see that I'm using the same, or I'm using a key in this ID column here, my teacher. This looks like a normal relation column, and this is my JSON. So you see the record for me, very idealistic data, and Blaine, which we had to buy to get him. And then we have the course information. And here it's important to say or to point out that this course database will only be stored one. We don't repeat it for every student that is attending this course. What a student will have in the array is just the ID that we're going to see. So this is our JSON course. This is Blaine's programming course. And also, if you look at this programming course, it doesn't say Blaine is teaching it. It just says T2 is the teacher. And if we look at our teacher table, we see that T2 is, so it's almost like in the relational world, it's just that these values are embedded inside the JSON. Okay, now we have.
Quick question.
Yes.
Is a blob not better? I understand that a clob can cause issues with encoding.
Oh no, sorry, say again, a blob can cause issues with encoding?
A clob, CLOB can cause issues with encoding.
Oh yeah. The reason I'm using CLOB here is that it makes it easier for me to print the values. And obviously a CLOB is a text value, so it undergoes character set conversion. So if you're running it on a, so JSON is always UTF-8. meaning it can basically support every character in the world. But if you run it as a Clob, then it will get converted to the database character set. So we always recommend to use AL32 UTF-8 to basically remain in the UTF-8 world. But otherwise, you could lose some characters, especially on single byte databases. If you use multi-byte character set, it's actually converted to UCS2 and should be fine. But Blob is also a bit more compact because it basically preserves the byte nature of the JSON. So yeah, I mean, it's Blob is better than Clob, and we even have a JSON type in 20, so that's even much better. So that's be one of the next Ask Toms, I think. But good question. Good. So now if we look at the student here, this is our Mickey Mouse guy, and you see the courses here. I'm just making references to the IDs of the courses. I'm not repeating any of the course information. This is our lazy student, no course. Now, if I want to do an update on my course C4, what was C4? C4 was, I think, yeah, C4 was math, and we didn't have a teacher yet. So I want to set a teacher. I'm using JSON merge patch here to set a teacher to T2, to update the start and end date, and also to inject a new field, which is the capacity of this course. So we're not only doing an update here, we're also doing a schema change. And I can use JSON merge patch for this because I'm updating an object. In the previous example where we have the array of objects, it wasn't possible to use JSON merge patch because JSON merge patch doesn't like arrays. And it's not us. This is basically merge patch is a standard operator or some standardized RFC, and I kind of think they forgot how to update arrays. Anyways, we're gonna have JSON transform for this. So now if I query this, we see the update has happened. We have now a capacity for this course. So something that was quite hard in this pure JSON model, where I said, well, how would I even add a capacity to a course if the course information is scattered around every student and teachers? But here, there's only one record for the course, so it is very easy to add this capacity here, and it's also easy to know where to go after to find out the capacity because there's only one value for it. So I don't have data duplication, I cannot have inconsistencies, I only have to update one record if I want to update something. Now the lazy student, well, that's the same as it in the pure JSON model. I just go to my courses array and check the size for 0. So this is exactly the same. Now if I want to find out which are my teachers associated with a student, this is where I go to the student. Then let's look at this record here. Where did we have it? This one. Basically, if I want to find out which are the teachers of the students, who are the teachers of Mickey Mouse, I have to go to Mickey Mouse's array here. I see these are these 3 course IDs, and then I have to go to the courses, do a join, find the teacher IDs, and then dereference those to find the teachers' names. So we do this here in 2 steps. I'm using JSON table to flatten this out. Now I'm getting a separate row for every IDs. So I'm back in the relational, what they call first normal form. Every column value is scalar. And now with this query in the with clause, I can do my normal join business like I've done in the relational model. So this is nothing else. I go to this is my inline view here, the student courses. I have my courses, my teachers, and then I express my join condition, and I get back the teachers of Mickey Mouse. And it's totally fine to do this because we are in a relational database. So we do have SQL, we do have JSON table. So this course is really not so much about like really a given product. It's really more about these different data models. So if you go to another relational database, you will find that they may have something similar to JSON table, for example, like a flatten operator or something like this. The other benefit of using SQL here is that I not only can I use it for queries, I can actually use it to to generate new JSON data. So let's say this is the information I'm interested in, but I want to send it to my web application or my Node.js mid-tier code, and that really likes to receive this information as JSON. So I take the same query, and in the select part here, I was just selecting these relational attributes. I replace this part and say, well, that's a JSON generation function called JSON object, and I can return now the same result as different JSON records. I could even combine them into one big array if I put a JSON array tag on top. So now if you look very carefully, you see, well, Blaine Cotter is repeated here. That is because he's giving two courses that Mickey Mouse attends, and we didn't see it here because of the distinct. So that's your homework, to make sure that there's also only one teacher, that teacher names are not repeated here. So you have to work with a subquery here and put a distinct on there. I just felt this is good homework if you like this. Now, what about constraints? I mean, what I've shown so far is that yes, you can do whatever is easy in JSON, you can do whatever is easy in the relational world, but so far we've not looked at constraints. So I could insert a student that attends a course that is non-existent. And since it's JSON, the database wouldn't know that, for example, if I insert this, let's say I'm inserting another student, and one of these values here is the course that is non-existent. So that would, or I have a teacher, and I say I'm putting a teacher or a value as teacher here, which is a non-existing teacher. Then again, I have kind of inconsistent data. So what can we do to also solve this? Well, it's getting a bit tricky here. So what I did here is first the simplest case using a virtual column. So I'm altering my course table, and I see there is a new column called teacher ID. And that is a virtual column. You can see this by this generate always. So it's evaluating a function on my JSON, and it extracts this teacher information. I should have put a query here, but basically for every, we have another column now, and that just extracts the teacher ID, and it's now looks like a relational column, but it's not stored. It's a virtual column, meaning it gets computed. So now I can, similarly to the relational world, I can just alter my table course and say, well, on this virtual column that we've just added here, the teacher ID, make that a foreign key that references my ID in the teacher table. So now if I wanted to delete from my teacher table, let's say I wanted to fire Blaine because it was getting too expensive, it would say, nope, you cannot fire Blaine. He is still giving courses. So that integrity is getting enforced. I can use virtual columns here because there's only one teacher per course. So similarly, this is another example. I'm adding another course, PL SQL, and the teacher is T17. Well, that insert doesn't go through because, again, the database is checking the integrity of it. This is an example of a course where there is no teacher, so that works. The virtual column would evolve to null, and null is fine. It kind of means unknown. So I am able to insert courses where I haven't found a teacher yet. So now this works using virtual columns because there is only a one-to-one cardinality between a course and a teacher. But what about the courses inside my students? So let's go back to this Mickey Mouse example. We see here that Mickey Mouse attends these 3 courses, and I couldn't use a virtual column to extract each of these course IDs. So the goal is again the same. I want to make sure that in this array only valid course IDs are being used. But I cannot use a virtual column because a virtual column can only yield us one value. So that's not a Oracle limitation or a product limitation. That is just how the way relational databases work, that a value in a column has to be a scalar value. So what do we do instead? I mean, we still just want to show a case how it's possible to solve this. So I created a trigger here that is executed before you insert or update a new student. And inside, I'm parsing my new data. I extract the array, I iterate over this array, and I'm using a subquery to check if this exists or not. And if this course doesn't exist, I'm raising an error. So this is, again, this is not an example to motivate you must do this or you better do this. I'm just showing what's possible in concept. And this is also not maybe the most optimal or most performant way to write it. It's just showing you that by combining JSON and the relational model, it is possible to do this. So now if I want to insert another student, and inside my course array, I'm putting in a course value that is non-existent. Now it's not a this foreign key primary key check that fails, but it's actually the trigger that's now saying, well, course C99 is not valid. If I correct this to an existing course, I can insert it. Good. Let's go back to these slides and summarize this a bit, what we've learned. I think the lesson is that the relational model is still quite powerful. New data models show up and people say, oh, now it's XML and XML will serve world hunger. And then a few years later, it's JSON and then YAML and whatever. In the past, what's always happened is that these models pop up. For example, in the 90s, there were these object databases and the relational model kind of absorbs it, supports it, simplifies it, and you end up with a database that supports multiple of these models. In the 2000s was XML, and we added XML type to the database. These days it is JSON, and we added support for JSON, and I'm pretty sure it was not the last data model that showed up, or the syntax for data model. I mean, a lot of these were just hierarchical data models in the sense of XML and JSON. So I think it's important for someone who works with JSON to really know what a hierarchical data model is and to really think about the implications when you come up with some way of creating your JSON that might look optimal for the current way of how you insert your data or how you want it back. It's important to understand that maybe down the line it's getting harder to query it, and I better combine some of these relational model aspects and the JSON model aspects. So this is the slide I probably have on most of my presentations. It's kind of our mission where we say, hey, we're JSON in the relational databases, and we, on the right-hand side, we both have the SQL aspect of it. We want to make it very easy for SQL kind of querying. That is kind of what I've shown in this presentation. And on the other hand, what I have not shown is this whole aspect of how your application communicates with the backend. And we have the SODA APIs for that. SODA API right now don't really support join. That's something that we're looking into. So some of the things I've shown here and which sound quite logical are can be modeled using SODA. So for example, I could create a view and then I could say I want to use the SODA abstraction layer to get it. So I should have said what SODA is. So SODA basically makes your database look like a document database. So instead of writing SQL, you can have a put and a get or update operations and or query operations where you just create like a template that is matched against your data and then it's being returned. Exactly. Yeah, that was my little history lesson here. I hope I have not promised too much on the moon stuff and people feel cheated on now. But any questions?
Will Oracle support GraphQL in the database as well?
Yes. Is this a question or is this a? Oh, will Oracle support GraphQL? Oh, it was not. It's a question. we already have some graph languages, but I'm not sure if GraphQL is among those. I believe that right now there is some effort from the standardization folks, not only Oracle, but generally in the database industry, to standardize on graph languages. So that is something I would look out for. I'm not an expert on these graph or spatial languages. I know we have support for these data models, but I don't know which languages we have. Sorry. But if you leave us your email or something, we could get you in touch with the right people and answer this question.
If you look up Dan McGann, he has a presentation on using GraphQL that's interesting.
So we do support it.
I don't know that we support it in the database, but
okay.
look for JSAO.io, I think is the website, and I believe he has some material up there on GraphQL. And one other question, can we join JSON with another relational table?
Absolutely. I mean, I also see the question in the chat. Can you talk about converged databases? I think this is one of these words describing something we've done for a long, long time. So I think the word converged databases is relatively new, but the concept is quite old for Oracle. I mean, we've always wanted customers to be able to store different kind of data and not in separate silos. So if you go out and you build it and you have a business problem to solve and you say some of this is XML, some of it is JSON, some of it is relational, some of it is spatial, some of that maybe even like images in a file system, whatever, and you build these different silos holding different kinds of data using different languages, then pretty soon you will realize that you need to write application code to do something like a join, or you have to deal with inconsistencies, or that something you have to worry about transaction that span multiple databases. So it can become quite a nightmare to run such zoo. So I mean, Oracle has been for a long time supporting different data models. There was even a time when CLOBs or especially BLOBs were marketed, that you could store your videos or your music files in the database. I think that was never something a lot of customers were using, but for XML, for example, we've seen a lot of people using XML in the database and then joining it with relational things. Or these days, we even see customers who use relational XML and JSON together in queries. So the idea behind it is Oracle supports these different data models, and they're supported in a way that's kind of like puzzle pieces that you can really combine them. Well, maybe puzzle piece is not right because not every puzzle piece works with the other one, but more like Lego. You have different Lego blocks, but they kind of fit nicely with each other so you can build what works. And then concept like a transaction can then span doing an update on a JSON piece, on an XML piece, and various relational tables. And it also means that not only are these data models supported in the same database, they are interchangeable. So you can turn your XML into relational or your XML into JSON and vice versa. So you can very easy go, not join this model, but even go from one model to the other. And then if you want to do this in a performant manner, then you just take your toolbox of DBA or database knowledge and you build a materialized view, for example. So does that answer, was that enough of converged databases? So there is a chat and a Q&A, right?
Yeah, there's at the bottom of the screen, you can see Q&A, which lets us...
oh, okay, got it. Okay, it's two things here, yeah. And someone was raising the hand.
Oh, I missed the hand raise. Let's go back there. Looks like Marlon Davis has a question. If you have a mic, I can turn it on and allow you to speak, or you can type in the Q&A section at the bottom or in the chat, any of those three options.
So Marlon Davis brought it up with the converged databases. Okay, there's one
okay.
more. I was agreeing. Okay, perfect.
All right.
Wonderful.
So I'm going to share the slide that I have here. So here's the link that you can use to get to the to Beta's LiveSQL presentation directly.
Oh, that's very easy to memorize that link.
Yeah, I wanted to leave it up for a second.
Or they could just go to LiveSQL and Google for Moon.
Another thing that we'll be doing, I'm going to edit the video description when we go to post this session, and it'll have some basically index points so you can go back and forth to the different topics. And I'll make sure that this link winds up there as well. So if you don't feel like typing that out or searching, check out the past session for this video, and we'll put the link in there. All right, any other questions? All right, then. We appreciate you spending your time with us on this, and hopefully we answered your questions. If you come up with some other questions later on, feel free to post them in the Ask Tom area, and they will get to us, and Beta will answer them.
And if you have any ideas for topics, you can always email. I'm not sure if my email is on there, but my Twitter handle is on there. So just send out a tweet, say Beta, talk about this, and I'm happily doing that. Yeah.
There's the Twitter handle right there.
Yeah. Wonderful.
All right, and thank you, Stephen, for putting the link in the Q&A section over there too. If anybody wants to copy it out of there, that's a good place. I guess I should have thought of that. All right, well, sorry about my loud typing at the beginning, and appreciate you all coming, and we'll see you next time.
Thanks a lot. Bye, guys.